Now let us do some question on gravitational field, on calculation of gravitational field. So please look at this question. A uniform solid sphere of mass capital M and radius small a is surrounded symmetrically by a uniform thin spherical shell of equal mass and radius 2a. You have a uniform solid sphere of mass capital M and radius a, and it is surrounded by symmetrically by uniform thin spherical shell of mass equal mass and radius 2a. Find the gravitational field at a distance of 3 by 2a from the center and 5 by 2a from the center. Okay, fine. So we have a solid sphere. Suppose this is solid sphere, and this is a shell. This shell. So this is solid sphere. It's completely filled with masses, and it is surrounded by a shell. So this is radius a, and shell has got a radius of 2a. Okay, both have got mass m. What in case of sphere, mass is distributed over the volume, whereas on the shell mass is distributed on a surface. And now we have to find out gravitational field at 3 by 2a and 5 by 2a. So 3 by 2a will be a point over here outside the sphere and inside this shell. So here also I can make use of Gauss law of gravitation. We can take a Gaussian surface. First of all, let's do a part. We'll take a Gaussian surface. Which is symmetric to the mass distribution and passing through the point where you want to find gravitational field. So I want to find gravitational field over here. So I'll take a Gaussian surface which is symmetric to mass distribution. So mass is distributed spherically. So I'll take a sphere passing through this point. So it will be like this. Sphere passing through this point. A concentric sphere, of course. It's a concentric sphere. A slight deviation. Let's consider it to be concentric sphere. So this is a Gaussian surface. This is a Gaussian surface, imaginary surface, which is symmetric to the mass distribution, the given mass distribution, and passing through the point P where you want to find the gravitational field. So I want to find gravitational field over here. It must pass through this point. So that gives you radius of this sphere. Right. So if you want to find gravitational field at this point, it should be Gaussian surface should be of this radius. Or it's better, let's try to find in general the gravitational field at any point P which is lying at a distance of x from the, or lying at a distance of r from the center. Instead of finding at 3 by 2a, let's try to get a general expression of gravitational field in this region. This is region 1, region 2 and region 3. Let's try to find out gravitational field in region 2, and then we'll put the value of r equal to 3 by 2a. That's a good standard way of doing the question. You find gravitational field as a function of r in this region 2. Region 2 means region between this sphere and shell, and then put the value of r equals to 3 by 2a. That will give you the answer, right? So now I'll try to find out gravitational field as a function of r in region 2. Okay. So we have taken a Gaussian surface of radius r such that r lies between a and 2a. Okay. So this is a Gaussian surface. So the flux of gravitational field across the Gaussian surface, flux means surface integral. Surface integral of g across this Gaussian surface will be equal to what? See, g lie radially inward direction, since g is always attractive, and we have taken a sphere. So the normal to sphere will be radially outward direction, and we always interested in outward drawn normal. Gauss law of gravitation makes it very clear that n must lie radially, outward drawn. N must be an outward drawn normal to what? To Gaussian surface. So g lie radially inward direction, n is outward drawn normal, and since Gaussian surface is sphere, so normal to the sphere is in radially outward direction. So g dot n would be minus g, and g is a function of r. G is a function of R, and R has got a same value at each and every point on the Gaussian surface. So G will be having a same value at each and every point. So G will be constant on the Gaussian surface. So when I say G is constant on the Gaussian surface, I do not mean that G is constant in the whole region 2. No, G is constant over the Gaussian surface. And since you are evaluating this integral on the Gaussian surface, so I can say G is constant for this integration, because this integral is evaluated on the Gaussian surface, and G is assuming same value at each and every point on the Gaussian surface. So G can be taken out. So this will be G into 4 pi r square. And what is the mass enclosed? Mass enclosed is the whole mass, the sphere. Mass enclosed by whom? Mass enclosed by the Gaussian surface. So now we can make use of Gauss law of gravitation. So it will give us minus G 4 pi r square m. So G is 4 pi gm, that is gm by r square. Minus sign shows attraction. So in vector form I can write it like this. Okay, now you want to find G outside. If you want to find G outside, then this Gaussian surface has to be, I have to increase the size of Gaussian surface. If you want to find G at say point P over here, then Gaussian surface should be symmetrical to the mass distribution and must pass to the point where field is to be found, right? So I must take a Gaussian surface which should be symmetrical to the mass distribution and passing through this point P. Okay, so let's enlarge this Gaussian surface. Oh, sorry. Or remove it. Let's do another Gaussian surface. Let's take Gaussian surface. This. So this is now Gaussian surface. If I want to find it, your gravitational field at a point outside, at a point P whose distance from the center is more than 2a. You want to find gravitational field at point P whose distance is more than 2a. So this is now Gaussian surface, radius r. Yes, in fact I missed it. See, gravitational field in region 2 I got it as what? Gm by r square. And then at r equals to 3 by 2a, your gravitational field will be simply Gm 9a square upon 4. Just put r equal to 3 by 2a, you will get your answer. Alright. Now let's find the gravitational field outside. Here also you see it's very similar. G dot n ds, G lies in radially inward direction, n is in outward direction, right? N is radially outward direction because it is sphere, so outward or normal is radially outward direction. Normal to sphere lies in radially outward direction. So this will be minus G ds, this will be minus G 4 pi r square. And what is mass enclosed? This capital M plus this M. The sphere and cell both are enclosed by this Gaussian surface. So it will be 2m. So as per the Gauss law of gravitation, so this will come out as G into 2m, or G is minus 2gm, okay, by r square. And you want the field at 5 by 2a, so at r equals to 5 by 2a, your G is simply, you put here r equals to 5 by 2a, that will come as what? 8gm by 25a square. So that's how you can find gravitational field. That's how we can find gravitational field. Alright? Okay, let's move ahead. Let's see this case. See this question. The density inside a solid sphere of radius a is given by rho equals to rho a by r, where rho naught is density at the surface and r denotes distance from the center. find the gravitational field due to this sphere at a distance 2a from the center. Okay, so this is your sphere of radius say a, and I want field outside. I want field outside, right? You can find field inside also, but I want field outside. So let's take point P. This point P is lying at a distance say r greater than a. So we want to find a gravitational field at a point P which is lying outside this sphere, right? So again we will make use of Gauss law. We can draw a Gaussian surface symmetrical to the this is Gaussian surface, symmetrical to mass distribution, and passing through the point P where you want to find gravitational field, right? So mass is distributed on a sphere, so a Gaussian surface which is symmetric to mass distribution would be a sphere only. And let's find flux due to flux across this sphere, this Gaussian surface. So G is inward direction, G is always attractive. Since I have taken sphere, so outward drawn normal is radially outward, so G dot n is minus G, and G is a function of R only, so this will be minus G into 4 pi r square. And what is mass enclosed? Mass enclosed is all the mass of this sphere, mass of this completed sphere. So how will you find the mass of this sphere? How will you find the mass of this sphere? Because rho is not constant, rho is varying. Rho is varying over here. So how will you find the mass? That's the question. How will you find the mass of this sphere? Radius they have given you. Radius is a. See, what I can do is, we are given rho, and rho is a function of r. So what I can do is, I can take an element of this sphere. I can take the element of the sphere in the form of spherical shell. I'll take element of the sphere in the form of spherical shell. Suppose this is spherical shell of radius x and thickness dx. So what is the volume of this sphere? Volume of the sphere is, I'll take a element of the sphere in the form of spherical shell of radius x and thickness dx. So what is the volume of the spherical shell? Volume of the spherical shell is 4 pi x square dx. And what is density of the spherical shell? Density of the spherical shell is rho a. This r is distance, so distance is x over here. This, so that is your dm. Get your point? See, we always take element in such a way where this rho can be regarded as constant. Whenever you want to find mass, you always take the element of the sphere in such a way where this rho can be regarded as constant. So I have taken element in the form of spherical shell of radius x and thickness dx. So all over this spherical shell I can regard this rho to be constant. So rho is rho a by x at this spherical shell at each and every point, and this is the volume d tau, rho d tau. We write it like this, rho d tau, where rho is rho a by x and d tau is 4 pi x square by dx, 4 pi x square dx. So this is 4 pi rho a x dx. So total mass enclosed will be integral of this dm from 0 to what? A is radius. So that will be 4 pi rho a x square by 2. So that will be 2 will cancel out. So 2 pi rho a cube. That would be the mass. That would be the mass. And we can yes. So according to Gauss law of gravitation, G dot NDS is 4 pi gm, and this is minus G 4 pi r square 4 pi G 2 pi rho AQ. So 4 pi will cancel out. So G will be minus 2 pi G rho. This. Okay, so this is G. In vector form, we can write it as 2 pi G rho. This. Okay, so ER is unit vector in direction of increasing R. ER is unit vector in direction of increasing R. Okay. Okay, let's do the next question. See, this uniform ring of mass m and radius a is placed directly above a uniform sphere of mass capital M and equal radius. Means radius is same as a. The center of ring is at a distance of root 3a from the center of the sphere. Find the gravitational force exerted by a sphere on the ring. See, we have a sphere, and above this sphere we have a ring. Like this. Above this sphere we have a ring. Alright, this is the center. Okay, so this is A, this is also A, this is root 3A. You have to find gravitational force exerted by a sphere on the ring. Okay, gravitational force exerted by a sphere on the ring. See, outside a sphere, the gravitational field is going to be minus gm. We have just found. Right, which is same as this gravitational field outside a sphere is same as if we have a point object over here. The gravitational field on the disk due to sphere is same as the gravitational field due to point mass kept over here on this disk. So gravitational field due to sphere outside, gravitational field due to spherical shell, gravitational field due to sphere, gravitational field outside the sphere, gravitational field outside the sphere is same as, is equal to as if you have a just point mass kept on the center. Meaning, if you have a mass m and radius a, then gravitational field over here is same as if we have kept a point mass of mass m over here. Then also gravitational field is same. The gravitational field due to sphere outside the sphere is equal to gravitational field due to point mass m kept at the center. Right? So that means gravitational field at each and every point on the disk due to sphere is equal to gravitational field due to a point mass kept on the center, gravitational field on this disk due to point mass kept on the center. Right? So that means the force exerted by the sphere on the disk is equal to force exerted by a point mass over here on the disk. Force exerted by a sphere on this disk is equal to force exerted by point mass kept at the center on the disk. Get your point? And from Newton's third law I can say the force exerted by point mass at the center, force exerted on the disk by a point mass kept at the center is equal to force exerted by disk on the point mass kept at the center. Newton's third law. Whatever force this point mass exert on the disk, same amount of force will be exerted by disk on the point mass. Direction will be equal and opposite. Force exerted by point mass would be in this direction, and force exerted by disk on the point mass will be in this direction. That's the only difference. And that is very easy to do. We already know this is not disk, sorry, this is a ring, we call it disk. So, and we know the gravitational field at this point into the ring. What is that? We have already found it. The gravitational field to a ring at a distance of x was what? Just recall, this was the gravitational field, gmx was the gravitational field. The gravitational field, so x over here is root 3a and r is a square root 3a whole square, so 3a square 3 by 2. This will be 4a square 8a cube. So that is the gravitational field due to a disk at this point. So the force exerted by disk, force exerted by ring on the point mass would be equal to gm root 3 8a square, and mass is same. Yeah, no, this is small m. Mass was, for the disk it was small m, and sphere it was capital M. For the disk it was small m, and sphere it was capital M. So this is gmm root 3 by 8a square. So on the point object it will be in this direction, and on the disk it will be in this direction. So force exerted by a sphere on this ring will be in this direction, and the magnitude is this.